So our next speaker in this portion is Robert Stroud from Tescan. He is the sales manager at Tescan for the Tensor Analytical 4D-STEM, a relatively new microscopy product, and he's going to tell us all about it.
I'd like to thank everyone for the opportunity to come and participate in your seminar today. I wanted to tell you a little bit about this tool that we've come up with at Tescan, and particularly aspects of it related to we good? Okay, to multimodal characterization and focus on diffraction techniques. Maybe just a real quick review. There's been a lot of slides talking about what is STEM. Kind of the main point here is the fact that you have a very small probe, that you can access an area of your specimen, you can get compositional information, you can get imaging of different types depending on where you place detectors. And then thanks to these new pixelated type direct electron detecting cameras, you open up this whole category of 4D STEM. And there's a wide range of things. Oops, if I can use the pointer instead of the, there we are. Yeah, so all these structural type information, things that you can access with the pixelated detector, phase and orientation, DPC, strain, virtual imaging, all sorts of things. Despite the ability to do that, implementation has been a bit difficult. For example, if you have a traditional TEM here, conventional, you have a multitude of cameras and monitors. And it's been difficult to work with all the techniques seamlessly. And what we've done is we've created a microscope that is fully integrated. So you manage all your detectors, all your measurements through a single interface. This is a Tensor in our lab in Brno, Czech Republic. And this is the actual interface that controls this microscope. And what that allows you to do is you can directly load the specimen. You can select where you want to start working. You can navigate, you can set zone axis, you can go to an area of interest, and you can go directly to a measurement without having to do any work with the optics. And if you're the kind of person that wants to work with the optics, it's all there. You can get to all of it. So it's at the simplest level, you can go directly to an analysis and start acquisition and have usable data. If you want to go in and do things at a lens control level or at something very specific, that's all available too. Show you here, I can work this thing. This is the host of measurements we bring in what we call Explore. So Explore is our user environment. So there's STEM imaging, there's EDX analysis, there's the orientation and phase, as well as strain mapping, all the virtual techniques, and then a host of tomography, real space, EDS, and 3D electron diffraction for solving structure. I guess I'm on this one here. And then we have a custom API for doing special experiments. And this is just an example of the kind of things we can do with an integrated microscope. So if I want to work on a zone axis, this is just at the initial steps. I can select a place in real space on my specimen. I can then have a corresponding diffraction pattern, and I can directly interact with the stage on that diffraction pattern, double-click on a zone, and the goniometer will set Z, and the microscope will be focused, and you can start working. And that just looks something, if I can figure out the controls, something like this. So you can see the alpha beta tilts labeled, and then you can go directly to a zone, and then you're ready to go. This is another example. This is just the orientation experiment, and it's just showing, it's slightly sped up, but this is more or less real time. And you can see as we start acquiring data that the solution's coming out. So conventional TEM with a standalone nanomega system, you have to do everything post-processing. We're able to do it all directly in line. I have a few examples I wanted to go through just to kind of give you a feel for what sort of diffraction experiments we can do. And I'll just kind of give you a feel there. And maybe as a bit of background, we use something called precession. I'm guessing most people in this room know what that is, but just very quickly, in case you don't, with TEM, because of the energies involved, we're having to deal with dynamical diffraction, which makes things like structure factor calculations not useful. Template matching doesn't work. So with the technique of precession, well known from 1994, Vincent Midgley, you push the beam off axis, you rotate it at high frequency, and you get a composite quasi-kinematical diffraction pattern. So we have a precession, dedicated precession deflectors in their column. We run at 72,000 hertz precession. So we're able to do all the setup and alignments and just button pushes with something that would take you 20 minutes or more on a conventional microscope, and your acquisitions would be limited to about 100, 200 hertz. So having the ability to work with diffraction patterns, it gives you things that maintain the geometry, gets rid of dynamical effects, gives you more higher order reflections, all the things you want to work with. I'm going to just make it jump ahead here. And so this is just an example of how orientation works. You calculate templates for your material. You compare that to acquired diffraction patterns, and then you're able to pick a solution. And so here's just a case. If you haven't seen what precession can do for your data, very simple orientation map with, I think, what is it, aluminum and BGO. And you can see there's areas that don't index properly or index incorrectly. So that's kind of the quick tour of why we do precession. So now let's talk about, because of all these techniques being fully controlled and integrated, what can you do with a tensor? So one thing that's interesting is using this sample. It's copper with a small amount of tantalum in it. The guys at US Army, thanks to Chad Hornbuckle's group there, they were studying this material and trying to understand why the grains weren't coarsening due to these high velocity impacts. They have an aluminum foil, they hit it with a laser, does something like 30 GPa of energy into the sample, but due to the tantalum, the structure's locked in and they don't see coarsening, so they're interested in that. What I would point out here is this was done at a fairly slow speed for us. This is 500 frames per second. We can go up to 4,500 frames per second, almost 10 times faster. And using now orientation as a navigation technique. So I can say, all right, where do I want to work? Let's just grab a very quick orientation map, and then maybe you're interested in these diagonal band-like structures. The researchers actually were very interested in these small grains here at the interface where the shock happened. And then you can use that as a navigation technique for deciding where do you want to do your higher resolution work. In this case, kind of a conventional orientation map, looking at the grain boundaries, the sigma 3s, and you can see some twins and different information. What else can we do? So multimodal characterization, because you have access to all the detectors, you're working in a kind of orchestrated way. You can do conventional type things. In this case, it's a phase change memory device, and from our friends at ST Microelectronics, and they were interested in this germanium here. Upon cycling, it seems that this starts to come out of solution, and they're trying to understand what's going on there in this region. And then if you take the diffraction pattern at every pixel, and you start to look at the difference between a phase map in this case and the EDS map, you can see that actually it is elemental germanium, and it's confirming this thing that they were working with of this germanium coming out of solution. Also, the way that these phase change memory devices work is they heat up to the amorphous phase, and crystalline phase is the on-off, so you can get a lot of useful information from not just phase, but orientation. Here, these tungsten lines, I think it's actually the guys at ST weren't sure why this was, but I believe it may be the position of where the fib cross-section was taken. You can see it's basically single crystal on the one tungsten line, and it's polycrystalline on the other. You can get other information if you do an orientation map. So in this case, you can actually see the set and resets in the material. And then another example, this is a semiconductor device that has a lot of activity here. It's a Samsung 5 nanometer we deprocessed. It's a FinFET. And so I wanted to share with you some things with thin films. Particularly, we can get imaging, we can get EDS, do very good work here, but we can go a little bit farther. So I wanted to work with this structure here. It's some sort of a tungsten plug. It's got a hafnium liner, some tinitride, so you can pull all that out with the EDS. And then what we can do, I wanted to use this to highlight the ability to work with multiple detectors, is if you try and study these two phases, this ti-nitride phase, and then a very similar cubic phase, this aluminum nitride here, that they're very difficult. You can see that conventional orientation or phase mapping has trouble with the phase that has aluminum in it, and it misidentifies it. So what we can do, and I'm going to switch phases kind of in the middle of the explanation because it's simple. Gold aluminum is about 1% difference unit cell. If you do an EDX map, the composition looks great. You do an orientation map, it's really nonsense because the software just can't differentiate. It's about 1% difference. Anything below 5% or so, even with precession, you can't differentiate between. So if you apply that chemical mapping to your templates, then because of the full integration of the system, we're allowed to do that. You can simultaneously gather all those signals, and then you get correct phase mapping. So if I jump back to our semiconductor example, we apply that same technique, and now you see that it gives very good differentiation of those two different films. And then this is some work I wanted to share. It was recently done, a lot of interest in the semiconductor community on ferroelectrics. There was a lot of talk about ferroelectrics today. So the hafnium, zirconium oxides, the challenge is it's a thin material. So you can see here, this is about 10 nanometer film of the hafnium, zirconium oxide with ti-nitride above and below. One thing I'll point out is we have very large fields of view. So this is like 1.2 microns. We can actually do this type of work with the 4D-STEM up to 30 microns. So we have very good beam tilt purity out at the end. I believe it's called purity, beam tilt. And so we have very large regions. We can do, instead of having to stitch things together, we can get it all in one go. The other challenge is that the people that put these films down are trying to select for a process that gives you this non-polar orthorhombic phase here, and there's other possible phases, monoclinic, you see tetragonal in the literature. There's also another orthorhombic phase that's because of the size doesn't have the ferroelectric performance, but the challenge is it has almost the same unit cell parameters except in one case. However, we can, using some precession and scanning with 4D-STEM, we can get some good statistics on what's going on at the grain level and showing that it's predominantly this monoclinic phase here and then this orthorhombic 29 of interest and a very small amount of the other non-polar version. This agreed very well with electrical data. And then the next steps in this study were going to be to try and start working more with orientation. Here's another view, a different region, same sort of, a little smaller, so easier to see what the grains are doing. But the next step would be to go and start trying to optimize the process to get the orientation to favor the direction for best ferroelectric behavior. So that's kind of a whirlwind of capability. A main message, I just wanted to show you what we can do, explain a little bit about our approach, and I guess if there was any questions, I'd open the floor.
Thank you very much. Well, I'll ask the first question, which is, have you looked at 2D materials using this system yet?
I believe that in our factory in Brno, there's been some work, but I haven't really participated with that, so I didn't have any great examples to bring, so I settled on films to share with you folks.
All right.
Yeah. I will say that we have ability to control the beam, so working with things that are very beam sensitive, we can get down to some very low dose situations, and we've been doing some work with samples that are very promising for managing dose.
All right, great. Does anyone have any questions they want to ask before we move on to our next speaker? And folks will be around after. If not, let's thank Robert again, and we'll move on.